just want to say some things. The restrooms are all the way to the left and to the right, the corner. We have beer, water, food. Please go ahead and serve yourself. I know we still have some shirts, but if you guys want shirts, there's still some shirts there, so please go ahead and get them. And that's it.
All right.
All right, John.
Awesome. Is we? She says we're good to go.
We're going.
Awesome. So this is pretty exciting. I'm really happy to be here again. We've got Dallas and Portland. They're actually going to be a bunch of people that are joining us. We're streaming this, so the whole thing will be recorded. It'll actually be up on YouTube after we're done. So if there's something that someone misses or whatever, for any other reason needs to go back and review it or needs to share it with somebody, it'll be online. So if we're new to this, so I might do it totally wrong and break something, or the audio might be crap, but hopefully it'll come out okay. So before we get into this, just curious, show of hands, how many people are already running Cassandra in production or messing with it in dev? Or okay, a few hands. People totally new to Cassandra? Okay, so a mixed crowd. Awesome. Is anyone using Spark already? Awesome. How do you like it? Good? Yes. See a thumbs up. 100% of thumbs were up. It's awesome. So first, before we really get kind of like, deep into how the two things work together, I kind of want to frame the problem a little bit so that we understand what the purpose is for these tools and how kind of we arrived at the system. Because without a little perspective on it, some of the stuff I'm going to talk about really doesn't make any sense. So the first thing that we're going to take a look at is this concept of small data. All right, small data is basically something that fits on your laptop that only you use. It may be a text file, maybe a SQL-like database. Generally, you're going to use tools like sed and awk to do processing on these files, and maybe some JSON. Maybe you whip out a Python or Ruby script. All right, you can do your analysis on it. You can iterate really quickly, and it's really easy to do. This is probably not a really great solution if you're looking to build a website, but it's really nice if you just want to do some analysis on log files or some data that you pulled off of somewhere. The next thing that we have is medium data. Medium data also, for the most part, fits on one machine as long as your hard drive is reasonable size. Most current web apps are, I'd say, in this medium data category. A lot of content sites. In my past, I've worked on a lot of these. One of them, we call it answerbag.com, and basically you can run on one reasonably sized MySQL or Postgres server for a while. You can do millions of page views a day, and maybe you put some caching in front of it or whatever. But your data is not so big that you need to spread it across multiple machines or really start to invest in crazy hardware. You can support hundreds of concurrent users, and you have the nice safety blanket of ACID, and it lets you do all sorts of really interesting operations. You get triggers and store procedures, and you can work with your data in a way that just feels safe to you. And one of the things that ends up happening is with this medium data situation is that you have to scale it vertically. So you either have to add more hard drives to one machine, or you need to get a bigger CPU once there's too many queries, or more network cards, or there's just a whole way like that you have to upgrade, or maybe you have to replace the machine entirely. So this is kind of the situation with medium data and scaling it. It's a very vertical process. But the challenge here is, how do we take a relational database, or really any traditional database that we're used to using, and bring it into the big data category? What do we have to do? How do we arrange our servers? How does it scale up? So the first thing that you'll find is that ACID is a lie. You cannot effectively have ACID in a database system when you decide to use replication. So let's take this example. I have my single master. And what we're going to do is we're going to introduce our client. This client is absurd, I know. And it's talking to the master. And this is okay. You're getting ACID, and you have isolation, and you can do your store procedures, and you're consistent. It's too much, I'm sorry. So let's say that your system is a very read-heavy workload, and you want to start scaling it. What you do is you then add, you have a replica here, right? MySQL land, we call this a slave server. And then you have your replication, And one of the things that you have here that most people won't tell you about is you have replication lag. So whenever you start doing a query over to the slave, you may be about 2, 3, 5, 30 seconds behind. So your view of this database is always going to be very inconsistent. You're going to do a write over here, and then you do a read over here, and you're going to get the old data back. And this is a serious problem because people will initially develop their application so that everything is consistent. They're only talking to one database. They probably develop in dev, not taking these things into account, because generally nobody wants to randomly develop against a server that's 30 seconds behind. So this is the first thing that goes. Okay? ACID becomes a problem. Your view into the database becomes inconsistent. The next thing that you notice is that third normal form does not scale. This is one of those things that you hit almost right away when you're developing a system that's under load. And the problem is that queries are unpredictable. And they take longer. The more disk seeks you have to do, the longer the queries take. And if the amount of data that you have, your hot data, is bigger than the amount of available memory, then it's also a problem because you're going to constantly go to disk, and you're constantly going to be paying that disk seek penalty, which is typically 5 milliseconds at the absolute best, all the way up to 15 milliseconds. So what you find is you need to start denormalizing your data in order to query it more efficiently. You don't want to have to query and join two tables. Instead, you copy things around. Maybe you copy my username everywhere because that's something that we display. And it becomes a lot more efficient because we no longer need to join two tables and do a ton of disk seeks. The next thing that we discover is that sharding becomes a nightmare. So sharding is the process of taking some of your tables that are on one database server and moving them to another database, or it could be breaking a single table up and splitting it between multiple servers. Both of these have their own sets of problems. For starters, you can no longer really do joins effectively anymore. If you take your user system, let's say you take your single database and now you split it into 4 systems. So now I have my users, my comments, my likes, and my messages. It becomes, or photos. Oh, hi, Daniel. It becomes impossible to join across the different database servers because they're separated in your application. You can no longer do aggregations because, well, the aggregations that you needed to do before probably relied on a join. So what happens is you end up denormalizing everything. You copy things around. You make it easier to query. Maybe you copy the same username again into multiple tables in different shards, and it's a lot more efficient. The next thing that you discover is that secondary indexes are problematic. So these are so much fun when you have one server, but as soon as you try and build a system where you have, let's say, my likes spread across 4 machines or 10 machines, and then you need to do a query to pull them all back, you end up having to talk to every one of these machines. So if you're doing 1,000 queries per second on your client, you're doing 1,000 queries per second on each of these servers. That doesn't scale with the number of servers that you add. You could have 100 servers, you're still doing 1,000 queries per second. So you have a very real cap there. So the only way to make this work is to now scale each of these servers vertically. The other things that are a pain, resharding, moving your data around. Now I say, oh, I'm going to move one of my tables from the first server over to the new 5th server. I have to manage that in my application. I need to know that maybe this data is not available here and I have to look for it somewhere else. And then on top of that, you've got schema changes. So schema changes are a pain to apply to, let's say, if you had 5 shards, 10 shards, 100 shards, you have to have someone that's managing that on each of the servers. It's error prone, so you have to develop systems around it to make sure that it works safely. And you're that guy. So the other thing that becomes problematic is high availability. And the reason for this is because your system is now very complex. You have this master-slave set up. Who's responsible to promote one of the slaves to a master in the case of a slave dying? What happens to all the data in that replication log that didn't get streamed over? Did you just lose 30 seconds of data? That's a problem. And effectively, it's a bolted-on hack. So downtime is definitely possible. If you're not dedicating massive amounts of money to it, it can be frequent. Anytime you're going to change your database settings, I'm counting this as downtime. OS upgrades, rack failure, data center failure. There's 100 reasons why a server can go offline. And having this be managed by that guy is ridiculous. The other thing is that multi-DC is also problematic with traditional consistent systems because latency is so high between, let's say, the coasts. You're really not able to take a 40 millisecond ping time and say, yes, I can absolutely do my write in 1 millisecond, have everything be synced across multiple data centers, and have a beautiful view of the world. It just doesn't work that way. So there's a whole bunch of failure here, right? We realize that trying to scale out is a pain because you're either scaling up and it's expensive, or you're manually managing all this data that's all over the place. ACID is the most overrated, impossible thing to have work at a large scale. You're just never going to be consistent. You may be consistent in the view of one server, but your entire system as a whole will never be consistent. So we might as well just admit that. Resharding, huge pain. We know that we're going to have to denormalize for performance reasons, and high availability is really complicated. So what have we learned? If we're going to make a new database from scratch, what would we build? Well, the first thing that I think we'd decide is that consistency just isn't practical. It's not going to happen. So we might as well just make the assumption that replication will happen asynchronously, and we're going to shoot for high availability in the process. Manual sharding is very difficult. We do not want to manage this anymore. Ideally, this would be internalized in our database system, so we can do that. What about all these moving parts? Now I've got master, slave, I have configuration things, I've got this web app which happens to have some scripts which move data around. Do I want to keep doing that? Not particularly. So what we're going to do is take away the number of moving parts and build a database where there's only one type of thing. It's just a homogeneous setup. Scaling up is very expensive. Vertically scaling, you're going to end up spending hundreds of thousands of dollars on new hardware. Your old hardware is now useless. What do you do? Put it on eBay? This is crazy. So what we want to do is use commodity hardware, and we just want to be able to add new nodes. If we want to double our capacity, we should just be able to double the number of servers that we have, and they shouldn't cost a lot of money. If we're spending $5 grand a server, that's pretty cool. If we're spending $100 grand a server, that's insane. And the other thing that we have here is our scatter-gather. This is those secondary index queries. We don't want to do querying every server. We just want to always hit one server. We want to hit one, let's say, partition on that server and be predictable, right? If we have an SLA to meet, we can't go query 100 servers at a time and get everything back and merge everything. It's unpredictable, so we don't want to do that. Right? We're going to denormalize. We're going to have great query performance. So that brings us to Cassandra. Apache Cassandra is a fast distributed database. The goal is to have high availability and linear scalability. That whole, I want to double the number of machines and get double the performance, that's what we get with this. We also want to have very predictable query performance. So we don't want a single point of failure either. Like I said, high availability. That means that out of all the machines that we put in our system, it doesn't matter which ones go down. We also want to put this stuff on commodity hardware. Like I said, $5 grand a server, totally fine. You don't need special RAID controllers. You're wasting your money if you go completely nuts on this stuff. And we definitely want this to be easy to manage operationally. We don't have to write 50 homegrown tools to move data around. We don't want restarting a server to upgrade the OS to take down our entire system. This should be something that I can go through and upgrade one machine at a time and fix, let's say, the OS version, and nobody should know. There shouldn't be a problem. So the reason why this works is because Cassandra is a masterless peer-to-peer system. Your data is going to be spread out around the cluster, and it's distributed automatically. You don't have to worry about where it goes, and it's replicated automatically as well. You give it rules as to how you want it to replicate. For instance, if you've got 3 racks in your data center, you can say, I only want 1 copy of each piece of data in each rack. That way I can lose a whole rack, and everything will be fine. Queries internally, you can query any node. So I can query this guy right here, and it's okay. It will know who owns that data. It will fetch it for me. It's obviously a little bit faster to talk to the right node, and the DataStax's native drivers will do that for you, so you don't have to think about that. But it knows. It's very aware. So it's just one giant cluster. Talk to any node, you'll get an answer. And then on our consistency, we have the option to tune it. So if we want performance, we can do a write, and we say, you know what, I know there's 3 copies, but I want to get a response back that everything's okay when only 1 copy has been written. And that's fine. And everything will be written asynchronously, and we'll wait for 1 response. And then as soon as that response comes back, we tell the client we're good. I mean, we can do other ones as well. We can say majority. We can say 2 out of 3, or we can say all. This one's low availability. Don't use that one. All is the worst. I don't know why it's there. But yeah, it's very, very tunable. So when we're doing our data modeling, we need to be aware of these core concepts. And this kind of takes a cue. Cassandra uses a language called CQL that takes hints from a relational database, from SQL. And you define tables, and you define columns, and they have types. And that's kind of where it ends. So at the top level, we have our key space, and then we have a table. And within a table, we have something called a partition. And what a partition is a grouping of rows. So the reason why this is cool is you can say, hey, I've got a bunch of rows, and they're all related. I want to store them together. I want to minimize the number of disk seeks. I don't want to have to go, well, I need these 10 rows back. They're all stored all over the place. Like, I'm now doing 150 milliseconds just in seeks. It's impractical. You only want to do 1, worst case scenario. So that's where that's useful. And the other thing is that we have clustering keys to determining the ordering of those rows within the partition. So here's an example. This is 1 partition out of a table that was groups. All right? Think about this as like Facebook groups. My group is ninjas. Okay? So this stuff is all 1 partition. All right? We've got our partition key over here. That's our group name. And we have ninjas that live inside this. And then we have our clustering key, which is our user ID. The rows are going to be sorted. When I do a query, I'm going to get back all 4 of these things in this order. It's very, very easy to use, and it makes queries very fast as a result. So the thing that you'll find with Cassandra is that you're denormalizing a lot, and the mind frame that you have to take is, I'm going to model my tables to answer my queries. So that's kind of the trick here. This is not the third normal form that you got used to. We're not going to be doing joins in here. We're always looking to be doing 1 query to extract a lot of information that has been very, very denormalized. So you can think of these as kind of like materialized views that you maintain yourself, right? And you're going to manage that in your application code, and that's okay. And then this is kind of what our create table looks like. And with this example over here is we have age as a partition key and user as a clustering key, and that's going to cause anyone with the same age to be clustered together in the same partition. Any questions before I move past this? None? Okay. So we do have limitations. You know, I've kind of bagged on all the things that come with a relational database, and I get to do that because Cassandra doesn't do any of them out of the box. So basically, we don't have aggregations, we don't have joins, and you're always going to want to look up rows by the partition key, so you don't get to just create a bunch of secondary indexes on everything, query, and not care. This is something that this was put in place because those systems don't scale, and so they're just not here. And you're not going to be able to do arbitrary full cluster queries. You can't do your full table scan over 100 billion rows. It's just not practical. So what do we do about that? Fortunately, I think you probably have guessed already, since this is a Spark talk, as well as Cassandra, that Apache Spark will be the solution to this. Apache Spark basically lets you do bulk processing of a ton of data. It's meant to process billions of rows from a variety of data sources. Unfortunately, Cassandra is one of those data sources. So at the most shallow level, you can think of it as a replacement for Hadoop. If you want to do bulk processing over, if you wanted to do something out of HDFS, you can do the same thing out of Cassandra. And it's actually a lot more than that. So the first thing you'll hear is people go, oh yeah, we can do bulk processing of a billion rows out of whatever using Spark. But it also does things like streaming. So you can be ingesting data into Spark. You can process it and then write it back into Cassandra, and it can be available. You can actually perform SQL over data that you're reading in. So you can take a table in Cassandra, and you can do full SQL on it. You can join against other tables, and it'll be a fully distributed system, or a fully distributed join. You can write these jobs in Scala or Python, or even Java. I don't have Java on there because I don't know why. I just forgot about it. It's okay. What's that?
Is your Python?
I do love Python. I'm like, oh, you can just take away Python. But you can do it in Java too. That's totally cool. I won't be mad at anybody here. It's going to perform really well. And then it also includes machine learning and this graph analytics. So GraphX is the graph library. Machine learning, it's called MLlib. So it comes with a ton of stuff out of the box. I'm going to show you a little bit about each of these topics in a little bit. And one thing I kind of glossed over, we have this concept of an RDD. When you're working with Spark, you have this concept of a resilient distributed data set. And that's basically a data set that can be spread over potentially hundreds of machines and operated on concurrently using these functional constructs, MapReduce, filter. So very useful. I'm going to show you a little bit how those work. Any questions before I move on? I love questions. Please ask.
RDD was what?
Resilient distributed data set. So think about if you were to have like a list, a huge list, and instead of processing it on one machine, you broke the list up into 500 components and spread it out over 500 machines. So you can apply a map, which takes a function, and you can say, I want to apply this map to every one of the elements in that list, and you can do that concurrently on all 500 nodes in your cluster. And then each one will have a result, and the list will be spread out across all the machines. And you can do the same thing with filter. So you can say, oh, I only want to keep the items in the list where my age is older than 52. No problem. Questions? None? All right. I mean, we're cruising through this. This is way faster than I intended on doing it. I would like some questions if you guys have questions.
How is the distributed thing different from Hadoop?
So Hadoop is a lot slower because it reads and writes things out of HDFS all the time. It's really built on kind of a, like a 15-year-old concept of how these problems should be solved. That's basically it. It's Hadoop is a very inefficient system for managing these types of computations. One thing to know about these operations is that they're going to be done in memory. So Hadoop, tons of I/O, like reads and writes each stage, each step of this process out. And Spark is just like, screw that. Like, let's be a little bit more optimistic. We're going to do everything in memory. Each RDD, each part of an RDD can be recreated. So if a server fails, that like part of that data will be reprocessed and recalculated elsewhere. So the job will just restart, not the whole job, but you'll get back to where you were. So the cost of a failure on a particular server isn't significant.
So in that sense, could I conceptualize it as you're both distributed batch processing, but one does it in memory and one does it in disk? So
well, a lot of what MapReduce does is going to happen in memory. It's just that each stage of the process in Spark will be in memory, as opposed to like MapReduce needing to write out a whole bunch, like do a whole bunch of I/O along the way. It's just a lot more efficient. I mean, the tests right now show that it's 100 to like 1,000 times faster for jobs, depending on the complexity of the job.
So we got a question is there a difference between Apache Spark and DSE Spark?
I'm not a pro on that. That might be a better you question, Adam.
Yeah, I mean, I don't think that there's too much differentiation between each. What the thing is with DSE Spark is it's tightly integrated with Cassandra. Is you don't have to build the ETL from one or the other. That's pretty much it. It's just Spark says
and how do you actually do that? A lot of people use things like Kafka, right? That kind of ingestion.
I will be covering Kafka on here, which is excellent because I love when people make comments that I'm about to show a slide on. Yes, I'm doing it right. Yes.
In the previous comment when you talked about designing data structures with Cassandra, you mentioned the normalizing the data query. But here we're talking about, well, if I keep my data normalized, then I can Spark to the group by and all of those things.
Sure.
Can that be done with relative speed?
So the question is, I talked about denormalizing your data for Cassandra, but here it's not. You're not seeing it as a thing, and that you do have the power of SQL. Do I get to avoid that? Now, the short answer is not typically. So the reason why you're going to denormalize for your Cassandra data is because you want to be able to serve up requests quickly. Typically, you have some sort of SLA, right? I have to complete every request in 10 milliseconds or less. Even if you were to use this process, you are not going to meet your SLA because the operation is so much more complex. You're not going to be able to say, I can do 10 milliseconds here, join 6 tables, perform 3 aggregations, and spit something out. That's always going to be orders of magnitude more complex than saying, hey, give me this one thing. Like, computer, give me one thing. Like, it's a, you know? So this is really great as a tool that complements Cassandra. So you've got your real-time stuff, and then maybe you say, I've got a ton of data that I've ingested. I want to roll up some aggregates. Like, I want to do daily aggregates or monthly or whatever. So that's where you use this. I want to do analysis over my whole data set. Yeah. Questions? Yes.
So how does it affect performance? It's a production in Cassandra. It's having traffic.
Yep. Yep. Question is, how does this affect performance? That, boom, is on my next slide. I'll just go right into it since you teed me up so perfectly. This is how you're basically going to want to set things up. If you've got a Cassandra cluster, and this is typically, this is about the smallest Cassandra cluster you're going to have, you're going to use the DataStax open source connector, and the way that it works is you've got a Spark slave process which exists on each of your Cassandra nodes, and you have a Spark master, and you submit jobs to the master, and it will go ahead and distribute the job to the slave. And the Spark worker will be talking to the local Cassandra node, and it's going to take advantage of data locality, which is nice. It's only going to get the data that's on this node. So it's not like you're doing some crazy query and everything's being sent all over the place. It's a lot more efficient network-wise than that naive approach. To answer your question, one of the things that's really nice about Cassandra is that you can easily run multiple data centers. Because it's such a different workload, you're typically going to want to have one. It may be a virtual data center, but you'll probably have one virtual data center for your real-time stuff and one virtual data center for your analytics work. And that's typically how things. That's the best way to do it. And you may have heard about this as like Lambda architecture. That is definitely the right way to go with this, because when you're doing these big batch jobs, you're just going to be scanning everything, right? It's going to be messing with your buffer cache. It's going to be just really eating up your I/O. So you don't want to do this on a system that's real-time. So you have 2 VCs, one real-time VC and one for your batch jobs.
So taking a step back, someone asked a question. Can you speak more about the Cassandra, the key space table architecture versus in respect to a relational database?
Sure. A key space is effectively the same as a schema, and a table is actually almost exactly like a table in the relational world. You can think of them as exact equivalents to each other. The real difference is the partitions and the rows. So you still have rows, but they're grouped together in partitions, and that's the main difference between that. They're also automatically spread out across multiple machines for you, so that's something that's important there. I hope that answers it. And
yeah, hopefully it does.
Yeah.
And then somebody's saying that we have both data in HDFS and CFS. Is it possible to query / join data from both sources using Spark?
Yes.
Cool.
Did you guys hear the question? They said they have data in HDFS and CFS. Can you join them? Yes. And that will appear on a later slide. But you can join data from different sources. So you could say, I've got some data in MySQL, some in Postgres, and some in Cassandra, and you can do a join across all 3 data sources. All right. Yes?
So this is making an assumption that the Spark is going to be deployed in standalone mode. That at least support resource is down.
Not well with this. I don't believe so. I'm not 100% though because I haven't used either one. Do you know? No. Okay. I wasn't sure if you were like making a mad face at me.
No, I was thinking.
Okay.
Yeah, I'm sorry. Could you go over what your architecture was again? Because I'm not seeing on the slide where the connector is and where the is being run locally and
The connector.
just the master.
Well, in this, it's hard to put everything on one slide.
Yeah.
In this, we have 3 Cassandra nodes, and on each one of these, we're also running Spark.
Okay.
And then there's a master that's like out here somewhere.
Okay.
I probably I should have added him.
I guess that's what I used.
Yeah. There's a Spark master running somewhere. This is only in the case of the open source side of things. If you're running DataStax Enterprise, then that's managed for you.
Oh.
And I know that you are, because we just talked about it.
No, I mean, I don't normally. But the enterprises that I consult with seem to always use it. So
Yep.
And I figured that it was the easiest way to get Spark. I didn't want to have to go and try to figure out how to install it and bring it up with this, whatever you were going to run through today.
Yeah, and that's one of the nice things about DSA.
So running Spark locally is for ingestion purposes back to the master?
No, running Spark locally is so that when you're querying, when you do a Spark query, each of these nodes is going to get the query, and this Spark process is going to talk to the local Cassandra. It's to avoid, as opposed to having it off on other machines and having a ton of network transfer.
Okay, let me ask Paul, sorry to dominate, but are you saying this is the Spark data center that we're looking at? We're not
Yes.
looking at the live real time.
Right, yeah. You would have another data center that looked like that. You'd have 2 virtual DCs. One's like this, one's like this.
So this one is your analytics center, and you're not showing us the real time.
Is that? I will probably modify the slide to have 2 DCs. So yes. Okay.
Another question.
Oh, sure.
Back more to just raw Cassandra. Is partitioning Cassandra the same as table partitioning in RDBMS's systems? And in what way can you define partitions? And is it only by the key, or are ranges permitted?
Okay. The answer is it is only by the key. It is nothing like partitioning in a relational database. In a relational database, I have this range of data that's going to live over here, and it's about the physical separation of files on a machine. Partitioning in Cassandra is about spreading my data across the entire cluster. So it's just each partition key will coincide to a particular server and be managed by that server. And if you add more servers, then that data may move to somewhere else. But yeah, it's only about where data lives, where a piece of data lives.
Yeah.
Cool. All right. So the first thing that I wrote, my first Spark job was data migrations, and I thought this was pretty sweet. How many people here have had to do their own manual Cassandra data migrations before? It can be painful. Because you've got 2 tables, and you're like, how do I move everything? How do I move 1 billion rows from here to here? And you write like a Python job to do it for some reason, like I would do. And it takes forever. And by the time you're done, it's like 3 weeks later, and you have a huge beard. I started my job without a beard. So Spark is nice because you can read all the data out of one table, turn it into a different format, and then write it out into another table. So in this example, we just have a very, very simple table. It maps the user to their favorite food. And my favorite food is bacon. I'm not secretive about that. I tell everybody. We've got someone named Dave. We've got Luke over here. Yeah, looking at you, buddy. We've got someone named Patrick. And what we want to do is we want to kind of reverse this. We want to create a little index here where we say, you know what, who likes bacon? And it's going to give us an answer, John and Dave. So I actually have code here which is kind of intense, and I'm really glad that this video is going to be online because we may need to come back to this at some point. But effectively, this is the entirety, or almost the entirety, of a Spark job to do a data migration. So this is more than, let's say, writing a insert into some table, select from some other table. But remember, we're dealing with potentially tens or hundreds of terabytes of information. You just can't do that. So we need everything to be distributed. We've got 100 servers here. They're all going to work together on this operation. So what we do is, the short version of this is we have our user table right here, and we have our Spark context, and we say this is the key space and this is the table. And then we run a map on it. And remember, a map is a functional construct, and what you do is you pass a function right here, and we return a new piece of data, right? So we're going to construct a new RDD. Remember, that's resilient distributed data set. We're going to construct a new RDD from this user table. And we use these case classes, and what happens is we return a new row for each user that was in this original thing. And then we can use this food index saved to Cassandra, and it's just going to go ahead and write this food to user index. I don't know if this is clear back there. I'm sure there's questions at this point because I'm just throwing code at you in a language that I have yet to introduce to the world for you guys. Does this make sense? Is this like a reasonable thing, or do you have questions? Yes?
What's that? Is the case class?
So I'm not 100% on the exact details on what makes a case class different from a regular class. It is just a really, really convenient, basically a convenient class that you can use that that Spark understands. Yeah, sorry. My Spark knowledge or my Scala knowledge is shaky at times. I know how to code it occasionally. Yes.
So count the getters, setters, and equals hash code.
I can't hear you.
It counts with the getters, setters, and things like equals and hash code.
I still can't hear you. I'm sorry.
Sorry. It counts with getters and setters.
Okay.
And things like equals, like deep comparison, and hash code.
Okay.
Predefined.
Oh. Okay. There we go. Comes with a bunch of stuff predefined for you and is awesome. The gist. I knew it was awesome. I didn't know about the rest of the stuff. Okay. Oh, yeah.
So how does this actually work between all the multiple nodes? How does the data get partitioned into clusters? Just from here, there's no index.
Right.
How does it know to just grab the table and divide it into
So that's a good question. How does it know how to divide the node into the data into multiple pieces? When you construct this RDD, this user table, that RDD is spread across the entire cluster. So if you had 500 machines, it's around all of them. Each Spark worker, when it starts doing a query, it gets broken up into multiple partitions, and each of those partitions is executing queries against its local Cassandra. So the way it partitions is just by taking advantage of the local data that's on disk. One thing I didn't talk about was something called vnodes in Cassandra, and vnodes actually end up being a really convenient way of partitioning our data automatically. So it'll take advantage of the vnodes and use those to form the partitions. Magic. Yeah, and the connector, the really nice thing is that the connector will do this for us. So by default, this Cassandra table, this comes from the import of the connector. So that this Cassandra table gets added to the Spark context automatically when we import the connector up here. Yes?
Does the solution modify the data one?
I cannot hear.
Does the solution allows us to modify the data while the migration?
Does the solution allow us? Yes, of course. Does it allow us to modify the data while we're doing the migration? You can do anything you want in this map. Any operation that you want to do in the map, like you can go nuts. You can do aggregations. I'll actually show an example of some aggregations that you can do. You can do, you could tokenize if you wanted. You can apply machine learning algorithms. I have some examples of those. So you can get crazy.
What I mean was, is it possible that another process will modify the data while going to modify?
There is an excellent chance that another process is going to be modifying the data. Now, one of the things that you want to keep in mind is how do you handle your data model? So if you're dealing with a mutable data model, then you just have to understand that if you're working on two things at the same time, there's a chance that one of them will modify the other. That's just one of the risks that you take when you work with a data model like that. Typically, when you do with Cassandra data modeling, what a lot of people will do is they'll just say all my data is stored immutably. For instance, if you're ingesting something, like a big use case for this, specifically applying aggregations, is if I'm ingesting time series data, I'm putting data in my database that's immutable. So maybe I'm reading cell phone GPS data, and then I'm putting it somewhere, and I want to do roll-ups on a minute. Well, you don't really, in that case, have to worry about your data changing because it's immutable by its nature. I would say most of the workloads that people use Cassandra for fall under that category. So it's the web. I'm ingesting a ton of stuff on the web. I want to do analytics. I don't know if you guys have looked into the IoT, the Internet of Things. We're ingesting tons of time series data. How do I process it? That's really where this comes into play, and it is extremely helpful. Yes?
I'm sorry if I missed something, but I'm still trying to understand how is it in memory. The data is still in Cassandra.
Your data is still in memory. So your data is still, yes. The question is, how is it in memory?
Yeah,
My data is.
Understand the concept of in memory.
So Spark. So when you do a Spark job, Spark is going to query Cassandra and just pull all of its local data that it requires into its memory and work with it in the JVM.
Okay, so for Cassandra, my data is still on the disk.
Yes. Yes.
So when a Spark job accesses my data, it brings it into memory.
Yep. It's just going to query it like anyone else would query data. In fact, it uses CQL, so it's not doing anything crazy. It has to obey all of the same rules that any other application does. It just reads a ton of data, which is one of the reasons why I say it's a good idea to put it in a separate data center. You don't want to say, like, hey, I'm going to do this crazy job, and I'm going to look at everything. That kind of just screwed up all my real-time stuff. Like, you just broke my SLA. So that's why you do two DCs. Yeah?
So you mentioned Spark supports SQL or format of an SQL.
Yep.
Could this have been done with just
Yes.
SQL-like select
Yes.
insert into?
Yes, it could have.
Is there any reason why you would do something like this?
I wrote this first.
Okay, got it.
This is the first job I wrote. This is actually on GitHub. So I wrote this as when I was first learning, and I needed a really short job. I mean, you look like it's 20 lines, and I have a space. I have a new line in between like every line of code. I don't know why I did that. It was easier to read. But yeah, you could have. This could easily be done with Spark SQL. Next slide. So the way that this would work to just roll and keep going with your question is you can have an RDD and you register it as a table. So you'd say, here's my table, register as table, and you give it a name, and then you can do select whatever, and you can do arbitrary queries across the table. You can register multiple tables. You can do, this is awesome. What's really cool is if you're using DataStax Enterprise, you can get a Spark SQL shell. So you can just open this up and you can just start doing queries against your tables. So it's.
Is that standard SQL as opposed to CQL?
It's SQL because this comes from, this is a Spark construct, right? And one of the things that's really cool about this is you could take other RDDs. So I could take an RDD to a Postgres database. I could do a join of MySQL to Postgres to Cassandra, and then blend that with like some other crazy, like with a CSV file if I wanted. Yes?
Can I join with MongoDB?
I'm not sure what the support in Mongo is for Spark. I don't know. I'm like, oh god, the question's so hard. I really don't know. My question would be, why are you using Mongo in the first place?
Well, because I get, not to defend it, but I get a little bit of it, a little bit of all of this without getting too much into.
Yeah. I'm just messing around. But I'm a little bit serious. So like I said, you can query anywhere you want. So this is convenient. Spark streaming. This is my favorite part of Spark. This is where I started using this, and I was so happy. I actually have an open source analytics project that I'm working on. Think of it as like a real-time Google Analytics. It's focused on getting feedback back to the user within 2 seconds of any activity that occurs. And I'm using Spark streaming to handle all of it. Basically, what Spark streaming is, you can read data from a whole bunch of sources. Kafka is the one that I particularly like, but you can do 0MQ, you can do raw sockets, and you can even do text files or CSVs or whatever. And the way it works is data is read in batches, okay? And you define the size of the batch. So maybe I've got a 1 second batch, and here's a chunk of data that comes in. And what I'm going to get is a bunch of a list of things that came in during the process of that stream. So here I'd say, oh, here's three pieces of data. What am I going to do with them? I'm going to aggregate them a certain way. I can do whatever I want with it. And then ideally, what I'm doing is saving that out into Cassandra. On my next slide, I'm going to show an example of this in action. But this batch, this window keeps sliding down, and you keep getting these micro batches of data. So if you want to say let's take my example where I say I want to get 1 second windows and I want to know about which pages are being hit and how many times they're being hit. Well, as this is coming into my analytics project, I can then aggregate into these windows, write my data out into some Cassandra table, and I'm good to go, and I have everything pre-aggregated. So, as I said, I love Kafka. I think that this tool is absolutely brilliant. People will say that it's a queue, but that is slightly misleading. It's actually a partitioned distributed commit log. There's some nuances in there that are very important. Messages are sent in here, and they're sent to topics. And the reason why this is different than a message queue is it really is more of like a pub sub. So you can have multiple, they're called subscribers. You can have multiple subscribers reading from the same topic. So I could have 500 subscribers to an individual topic. And things in a queue are typically removed when they're processed. Not in the case of Kafka. They're going to sit around for a little while. And each consumer is going to maintain its own position in that queue. So it's good to know the distinction between the two. In the case of using it here, it's probably not that big of a deal. What do we got? Yes.
One is that as of right now, there is no Mongo connector for Spark. A user looked that up.
Nice.
Or whatever.
I love it. People getting involved.
Yes.
It's not just one man.
Person that, coming back to the connectors, I'm wondering if they can use Spark as a server. Basically, like how you connect front end to our relational database.
Yeah.
Can you do that with Cassandra and Spark?
So there is a way to do it, but it's you would need to use something like there's a open source project called the Spark Job Server. It's from Uyala. Effectively, what you can do is you can submit jobs over a REST API, and you can get responses with that REST API. Without that, it would be very difficult to treat it as like a front end to a database. Now, if you're using that job server, typically you're going to take advantage of its cache, so you're going to be your data is going to be frequently out of date. So if you're looking to get like real-time updates to stuff, you're much better off just using streaming and writing it out to Cassandra, and when you need information, talking to the local Cassandra.
I'm just curious, why don't you have Zookeeper in the mix here? Is that necessary?
I have Zookeeper because it's a dependency of Kafka. This is the Kafka diagram. I did not create that. I just stole it. Yes.
Sorry. Is the topic limited to the one machine or the distributed topic?
Distributed. So a topic is partitioned.
Okay.
So if you want to get high concurrency through Kafka, you have to create additional partitions for a particular topic. This is a little bit tricky because when they're moving between machines, the client or the subscriber needs to be aware of them, and the high-level Kafka consumer, I believe, is aware of it. There's a low-level one where you get exposed to like all the nitty-gritty details of it. It's a little bit more hardcore than I'm interested in right now, so I don't use it. But yeah, that's how it works.
Is that in the data stacks, the DSE?
No, this is a standalone thing. But the thing to keep in mind is that there's a whole bunch of different queues that you could use with this. So you could hook up, you could use Spark streaming with any queue, or you could use it with Kafka, or you could just build your own with ZeroMQ. So it does fit the recipe of a really amazing Apache project that scales really well. But as far as I know, there's no plans to include it.
Now, Zookeeper is all file system based, right?
I'm not a Zookeeper professional. I try and avoid it.
But that's why I was wondering, is Kafka entirely file system based?
Well, okay, the question is, is Kafka file system based? I mean, it's writing its information locally, so it uses the file system. I mean, I guess that would make it file system based.
But it's doing it in memory. That's what I'm getting.
Well, it's writing it to it's writing its information to a commit log on disk. All right, I'm going to move to the next slide. Not the electric slide, but here we go. So taking a quick look at streaming. This is some more code, another 20 glorious lines. One thing that's interesting about streaming is that when you write these jobs, it's not obvious that it's looping over something because it kind of hides that from you. And that's a little bit tricky at first. So basically, you create this D stream over here, and I just happen to call this, you create this D stream, and no, that was it. And what happens is each of the operations that occurs along the way that changes, that mutates this RDD, it's effectively collected and then looped over in Spark for you. And I don't have the line here. There's a line above where you define the batch duration. But what happens is this chunk of code gets executed every single batch window. So you get a chunk of data, you do this stuff to it, and then you start over and you get a new chunk of data. This is from my Killer Analytics project. So if anyone wants to take a look at the full whatever, it's here. I'll post these slides on SlideShare, and again, the video will be online, so everybody will be able to take a look at that. Does that make sense, or did I just butcher that? What do questions? Yes.
I don't know whether it's on better or not, but what you said is you return the running batch by batch, and you are going to process each batch sequentially.
So you can do the flexibility of this is well huge. You can do anything you want between here and here, and it'll all get processed for every batch. So in this particular case, what I'm doing is this is some JSON data, and it comes in as a string, and then it extracts some JSON, and I have some JSON data, and then this is doing aggregations, and then this is writing it out to Cassandra. So every second, I'm going to get a bunch of data, aggregate it, and write it out to Cassandra in a bunch of different partitions. So the nice thing about this is I'm doing at most one, well, not one query, but I'm only writing my data in once a second. So I could be processing like 5 million events a second in Kafka, and the overhead's not enormous. So there's a couple things to keep in mind when you're doing this. I don't know why I picked that guy.
Very thoughtful.
That's what I think I Googled thoughtful old guy, actually.
It seems bad.
Yeah, he has no. Well, he's looking over here. He's like, what do I need to remember about Spark streaming? There are a few things. So streaming aggregations are an approximation. They're not perfect. So there's a good chance that you're going to want to go back and re-aggregate. But if you're looking for real-time numbers to show someone, it's okay that it may be like a little bit off, or your windows may be slightly not perfect. But if you do need perfect windows for reporting, you're going to want to go back and write a job that actually looks at all the data, re-aggregates it. So in my particular project, I have one that just has real-time data aggregated, and then I have my other data that has batch jobs that gets re-aggregated. If you are doing a ton of stuff with time series data, you're going to want to take a look at this. It's called date-tiered compaction. Unfortunately, we don't have enough time to cover every little nuance of Cassandra, but if you've got time series data and you want to get rid of it at some point, this is something for you to, that's a little homework.
Question.
Yes?
For streaming, is the event defined only as a time slice, or can it be defined as number of messages?
Time slice.
Just a time slice.
Yes, has to be time slice. It's batch in, its duration in seconds is the parameter. Yeah.
There's just so many ways to take the real stream and dice and slice it. You got Spark, you got Storm, Storm.
Yep.
If I'm reading real stream from, for example, I'm reading real data from Kinesis, or I'm reading real data from Kafka.
Yep.
And I need to aggregate it and do stuff with it. What's the benefit of using one over the other? I know there's completely different.
Storm versus Spark streaming.
Yeah.
Storm is more suitable if you've got if you're looking for sub-millisecond decisions based on individual events that are flowing through a system. Storm is the way to go. Unfortunately, you have to use, I believe it's called Trident, in order to set a few things up, and the operationally, it's a little bit more difficult to run, but you get the advantage of you're not doing microbatches, you're actually processing tuples as they come into your system. So it's like live processing. So if you're building a high-frequency trading system, Storm. If you're okay with getting 1 second windows, Spark. And to be honest, Spark has, in my opinion, a richer programming environment. So that's kind of why I'm a Spark guy. It's a lot easier to work with. It comes with a ton machine learning. It comes with a ton of stuff out of the box, and you can use it for everything, not just stream processing. You can do your bulk processing, you can do stream processing, you can do graph analytics, and you can do machine learning on it. It's kind of amazing. So that's my take. And I just changed these slides just now while I was talking. So we got machine learning. Couple things that we can do with this that are really useful. I picked out my favorites. So we can do clustering. Clustering is really nice if we want to identify different groups of things. So this is from the IRIS data set. It's like a data set that everybody uses for introduction to machine learning problems, but you can see that there's distinct groups of things, and it's possible to just say hey, go ahead and identify the different groups in the system, and it can make a pretty good run at it. And typically, if you're going to do that, you're going to use something like k-means clustering or one of the other machine learning algorithms that are available. And you would say, identify the 3 or the 5 or the 10 groups that are in the system, and it will just go ahead and do that for you. And again, since it's using Spark, it's fully distributed, so you can do it where you have massive data sets, like hundreds of millions of rows or data points. You can do power iteration clustering, which is nice to do clustering vertices in a graph. So there's a ton of algorithms in there for clustering, and I'm definitely not a pro, so you'll probably stump me with reasonably trivial questions. You can try if you want, or I can just move on. Yes, moving on. Logistic regression. This is really cool. If you want to have predict a binary response, like, will this senator win this election? And you can have these data points, and it will help you figure out answers to whatever you're looking for. It's a yes or no question. And you plug a ton of features in, and it goes ahead and does a bunch of crazy distributed linear algebra and gives you answers, which I don't understand how it does it. But it's there, and you don't have to actually understand all the nuances of it, which is pretty exciting. And this is available in streaming, so you can be pumping data. This is, I'd say, a great example of something that, do you want to implement your own logistic regression in Storm, or do you just want to be like, oh wait, I got like 10 lines of code and I can do it in here. And in this particular case, you might not care about getting sub-millisecond response times. You may be totally fine with 1 second. Like, it's it's pretty legit. And considering the latency, just going around like sending a response somewhere, there's a good chance that you're going to get 20, 30 milliseconds of latency. So, who knows? You probably don't really care most of the time. This is the really fun one. So if anyone wanted to build a recommendation engine and you're not sure how to do it, collaborative filtering is for you. Spotify did a talk at the Spark Summit about how they're using this to do song recommendations for their music system. So Amazon does collaborative filtering, like Apple. Everybody is doing this. I don't know if they're all using Spark for it, but I know that Netflix is publicly trying to move all of their infrastructure away from MapReduce, Hadoop, over to this. So this is the perfect match for Cassandra, because you've got this live hot data. You have people liking stuff. You've got people buying things, and you want to be able to build recommendations very, very quickly based on the things that people are buying. Someone adds something to their cart, and then what else can I recommend for this person? So this is a phenomenal system. And you get this feedback loop, and you get better and better recommendations over time. So this is an important question to answer, because a lot of people kind of mistake Cassandra for something that it's not. We always have to remember the true purpose of Cassandra is it is a really, really fast distributed database suitable for projects where I've got really, really tight SLAs. Cassandra is not a data warehouse. We're not going to say, how do I put 50 terabytes of data on each machine and never touch it. That is a total waste of a great piece of technology. It's really not its strong point. So if you're looking for a data warehouse, it's not this. You don't want to be doing this process. You just want to store your data in Cassandra in multiple data centers distributed around the world, and then use Spark for the analysis of it. You want to do streaming, get that batch processing. That's really kind of the sweet spot. It's moving away from this. I've got all this cold data, and I need to bulk process it, and 3 days later I get a response because my MapReduce job is just ridiculous and keeps dying and has to be restarted. No, you want to get everything real time. And that's kind of the sweet spot. So you've got two options. You've got two options when getting started with Cassandra, and Spark for that matter. You can go open source. I don't know how many of you like to tinker around in the internals of databases. I'm one of those guys. I actually find it to be really fun, and I know that's kind of weird. I like bleeding edge stuff. I'm okay if something requires me to go on IRC, use the mailing list, talk to developers, figure out what's going on, file JIRAs. I put JIRAs in all the time now. If that's you, you're an open source guy. Cassandra.apache.org, download it, just run bin Cassandra, you're good to go. But if you're going to run bleeding edge stuff, just be aware that you need to be part of the community to help improve the product. If you're more interested in sitting back, buying something, get support, SLA, then DSE is probably the route that you'd want to take. It's battle tested. We put this thing through hundreds of hours or thousands of hours of QA. It trails behind the latest release because it's just more stable. You can get it for free if you're in a startup. And yeah, I mean, the goal here is to come up with a stable release that's for enterprises. And It's integrated with Spark. So if you get DSE, then you have Spark, and you have also Solar integrated as well. So you get one thing, and you can do search, analytics, and Cassandra all with one product across multiple data centers. So those are kind of your two. Those are your two options. And that is all I have in the slides. Yes, not bad, right? We have more questions. We have any? Nothing from you? Nothing online. Yep.
So I saw that you're streaming as the technique for getting your data out of your running Cassandra into the Spark side of things. But how do you actually do that? You're saying that Spark should be in another data set.
Let me rephrase what I said. When you're building an application, typically you're going to write data into either Cassandra or Kafka or both from your application. So, for instance, from the analytics, my analytics system, I have a high-level producer open, and I'm constantly pumping messages into it. So as requests come in, I push data into Kafka.
So you kind of have to design your application with this in mind up front. You can't just turn it on and decide to do scratch.
Correct. Yes, you definitely have to deliberately design your application to be a streaming app. Yep. And I have, I think I mentioned it 1,000 times. I've got my Killer Analytics, which the goal is to provide a good reference app for people that want to do batch streaming, machine learning.
That's on your GitHub?
Yep. GitHub username is Rusty Razorblade. And my Twitter name, in case anyone wants to follow me, no big deal. Everyone does. Everyone already does, so I don't expect any followers.
So what does your killer app do?
Well, it's a real-time Google Analytics. So you're, like, right now, it doesn't do much of anything because I'm terrible with JavaScript, so I'm limping along. Like, I can write Spark jobs, and then it comes to, like, trying to display a chart, and it's 3 weeks in, crying. If anyone wants to be part of Killer Analytics, then go to JavaScript. I have a free, non-paid position open. Question? Yes, had something? No? Nothing? All right. No questions.
Wait.
No?
Actually, we got one. Why is Cassandra not a data warehouse? Why not use it for analytics? Are there any shortcomings? Which Hadoop distributed storage system is a good alternative to RDBMS data warehouse?
I mean, if
one of those.
I'm not a data warehouse guy. I can tell you that you won't be able to get the density that you want out of Cassandra, and it really wasn't built to be a data warehouse. So it's also not going to perform as well as something like HDFS, which works, or HBase, which for data warehousing purposes is going to be faster. But for real-time stuff, it's not even going to come close. Like, it's okay if you've got 25 moving parts in your data warehouse and it just falls apart and it's down for 6 hours. Nobody cares. Well, someone cares, but it's solving a very, very different problem. If we're solving I've got tons of data and I'm moving really fast and I need answers really quickly, you're gonna want to go Spark. But if you can take 6 hours of downtime, then Cassandra's probably not the tool for you. Yes.
So adding to that, it's also known as things originally Cassandra. So the density for originally Cassandra is not as high as originally Hadoop or anything.
Right.
So it would be more expensive. You would need more machines for the same.
Yeah. Sorry, I just throw out node density and I forget. Node density is the amount of data that you can put on each machine. So typically, when you do these Hadoop boxes, you end up throwing just crazy amounts of hard drives at it and just letting it go. But with Cassandra, it's a totally different mindset. It's like I'm going to put maybe 5 terabytes of data on each server. So it's just a different way of like looking at your data, a different way of processing it, and a totally different set of optimizations. Yes, Daniel.
Python guy. Did you try looking at the Python stack for Spark, and how would you compare it to Celery?
Well, they're definitely solving different problems. Celery is just a distributed job queue as opposed to streaming where you're just doing batch processing. I mean, in the example that I'm thinking of, there was, you have a celery task and it goes and it does something in the background and then it sends out an email. I mean, it's really kind of like a core part of your application. It's just that you want to do it as an asynchronous process, as opposed to streaming, which is analyzing a stream of data which is flowing in and manipulating that data and then saving it back into Cassandra. So I would probably have both systems in place, because Celery is extremely useful for, sending out emails or anything that's just too slow to go out in real time.
There's a very poor analogy to MapReduce and Celery for chords and chords. So that's the closest Celery can actually come to MapReduce.
Yep.
But at the same time, with Spark, all your code base technically sits outside of your application. Just push on a chunk of code into the Spark platform.
Yeah.
Without having the
Yeah. Yeah, it's definitely a little disjointed. Like you don't get the tight integration that you would if you were using Celery, especially if you're coding up Spark jobs in Scala. Even if you're coding them in Python, I didn't write an integration with CQL Engine yet, so you can't. It's not like you can define models. So let me back up a minute. So a former coworker and I, and Daniel has some commits in there as well, wrote the object mapper for Python for Cassandra. So it's called CQL Engine, and it's actually going to be released in the native driver. So CQL Engine will cease to be a thing on Monday, or it won't cease to be a thing, but it will be just sitting there for a while. And you can't use the CQL Engine beautiful models with Spark yet, but I would not be surprised if that was coming.
How far are we from having SQL models to be written?
That's what I'm saying. Is I don't think.
Is it a stretch at this point? Or
I haven't looked into it, but my guess, since I haven't gotten too many Python jobs running, is probably not today. I don't think it would be that insane, especially since you're getting, like if you do a Python Spark job now, you get a dictionary back, so it wouldn't be that hard. It's just that the way that the data is saved back to Cassandra, like if you just handed it a bunch of models and you were like, just save, it wouldn't know what to do. Sorry to everybody, that was kind of random. I hope it wasn't too. Yeah, awesome. Thumbs up.
So we get a question where we can actually pitch. The question is, where can somebody get the cool T-shirt you're wearing?
This is a sick T-shirt
with the winky emoticon.
Yes, with the winky icon. But let's just tell them to have them email you. We can send them not that specific shirt, but
not the exact. Keep the shirt on.
Not that big, yes.
He will.
Yeah.
It's not your shirt.
But this is actually that comes from what, Cassandra Day? That was.
Yeah, I think. I don't know which one. I don't know what this is from.
No, that was not Cassandra.
Well, no, that's not LA.
Not LA, exactly.
No, that's not LA Cassandra Day, but that is. I think it might have been.
Well, we have a lot of.
We didn't have one though.
Oh, but
I don't know what this is from.
But
I just found it.
So to make this a shameless plug, if you guys have not heard, we're having a huge event called Cassandra Summit up in Santa Clara in September. It's a 3-day event. So be sure to get involved in that.
Yep.
If you want.
Yeah,
Santa Clara, we're renting out a theme park.
Yeah, last year we had 2,500 people. I mean, it's the Cassandra event of the year.
Yeah.
For those of us that are enthusiasts,
Your shirt's from Strata. That's what I said.
Oh, cool.
Yeah.
But also we do events, and we do specific on-site visits too. So I mean, we go on to many different organizations and bring T-shirts. There's a lot of ways to get T-shirts. Yeah. You can always just ask nicely.
Yeah, seriously, just email. Actually, follow me on Twitter, and then ask for a shirt.
Or what we can do is somebody's probably going to put their T-shirt tonight on eBay, and we'll just give them your ID.
Limited edition.
Never been worn.
There was one more thing that I will get yelled at. Oh, I remember. If anyone is interested in speaking next month, I've been doing them a lot, but it doesn't always have to be me. I would love it, or we would love it, if we had some people that are using Cassandra in the field, maybe talk about some of the things that you're using it for. It doesn't have to be a long talk if you don't want to talk for a long time. Half an hour. Love to get some people up here that are, have put it in production and have some advice for everybody and want to share kind of the product that they're working on. I think that would be amazing. So yeah, and you don't have to be humongous. You don't have to be Spotify. I don't know if anyone's here from Spotify. I don't think so. So I guess that's it for me. Thank you.